typo, hopefully. I think it's the typo. Yes, it's the typo. Okay, so in terms of reading, so we should have read chapter 3 in this book. And also what we're going to be doing today is covering the method of types, which is something that is actually in chapter 11. It's chapter 11, section 1. And you might think, why are we doing chapter 11 first? Because essentially it's sort of a generalization of the asymptotic equipetition property, and it's a nice thing to do right after. And it doesn't really depend on anything before, other than the asymptotic equipetition property. So we're going to do section 11.1 next. Homework 2 is due tonight again on Canvas. I hope people have started it. Raise your hand if you've started it. Okay, good. The other thing I wanted to announce is that so we're having office hours Tuesdays, so Tuesdays today after class from 4:30 to 5:30. And I'm going to try, there's actually something in Canvas called the conference system. I don't exactly know how well it works or anything, but what I'm going to do is I'm going to open, assuming my laptop's disk hasn't crashed again, I'm going to open Canvas, Canvas conference, and supposedly from wherever you are, if you've got a laptop or something, you could go and join the conference and come to office hours virtually as opposed to physically, or you could come by in person. We'll see how it works. It's the first time I've used it, so I don't know. Okay, so let's get right to it and do the review. So remember we were talking about source coding. So source coding can be seen as a form of compression. It is, in fact, compression. Compression is a form of source coding. And the idea is that we have source messages, which are length n. We have n source letters in each source message. And what we want to do is compress it down to a sequence of m bits. So if there's m bits, then there's two to the possible code words. What we said is somewhat naively, if we want to make sure that all possible messages can be represented in a code word, we need to make sure that the number of source messages m is, the number of code words m is greater than the number of source messages k to the n, which basically asks for this criterion here, m greater than log k over n, which basically leads to sort of this lower bound on our rate, this very trivial, simple lower bound on our rate of log k, bits per source message. And what we said we can do is do much better than just log k, because log k can be seen as the upper bound of the entropy of the source messages. It's the entropy of the source messages when the source messages are uniformly distributed. But in general, source messages, and in particular source letters, are not uniformly distributed. If you take, for example, like the English language, and you take the characters of the English language, characters like the character E is much more frequent than the character Q. And so it's clearly not a uniform distribution over English characters, and so therefore we should be able to do better than log k bits, which is in this case 5. And so one way we can do this, in some sense, is sort of throw away those very, very unlikely source messages by doing this. Another way we can do this is essentially, which is the next message, is use sort of long code words. We use long code words for the improbable ones, and short code words for the probable ones. And this gets into this picture. And we last time actually had a code for this strategy, where we essentially use the typical set theory to sort of code for, use short code words for typical sequences and long code words for atypical sequences. Typical set theory is basically based on the asymptotic equipetition property, which basically says that when you have an IID sequence of random variables, that if you take negative 1 over n of the log of the probability, it converges in probability to the entropy, thanks to the weak law of large numbers. And we also define the notion of a typical set. So the typical set are the set of sequences of length n that have probability sandwiched between these upper and lower bounds of equation 5.22. And so graphically, here's the upper lower bound, and here's the log probability. And so the log probability has to be between plus and minus epsilon of h, basically, which is what that picture shows. And we also looked at a number of properties of the typical set. The first property was basically just saying that they are, that it's based on the definition. The second property says that there's a lower bound of close to 1 for the probability of the typical set, which basically means that if we define the typical set using this parameter epsilon, We can make epsilon as small as we want, and essentially we get all the probability. And also we have an upper bound on the size, which basically says it's 2 to the nh, and a lower bound on the size, which also says it's roughly speaking 2 to the nh approximately. If epsilon is small, then that's a 1. It's almost a 1. So basically the probability is about 2 to the negative nh, and the size is 2 to the nh of the typical set. Okay. And so our coding strategy was to partition all sequences, right? So these are all sequences here. This is the number of possible sequences. It's k to the n. And we partition this set of sequences into 2 blocks. One block is the typical set, which is the green bit, and the remaining, the atypical set, is everything but the green. Okay. And again, each dot is a sequence. And then if we encode that, so the typical set we encode with a bit string of length 2 times h plus e plus 2, or sorry, n times h plus e plus 2, where h is the entropy, epsilon is something very, very small, and 2 is just a constant. And then we encode the atypical set with essentially log k bits, which is this bad rate. Thanks to the properties of the typical set, that the typical set gets essentially all the probability, the atypical set eventually has probability less than epsilon, no matter how small epsilon is. And so what we end up getting after we sort of redefine a new version of epsilon, which can be made as small as we want by making the original epsilon small, or making the block size, the number, the length of the sequence, n, big, we get something which basically says we can encode at a rate. To get the rate, we just divide this quantity, this last quantity, by n. To get the rate of h plus epsilon, for any epsilon greater than 0. Which means that we can code, if we use a long enough sequence, long enough block lengths, we can code for down to as close as we want to the entropy. Okay, now, let me just, right. So this is Shannon's first theorem. And, we're not actually explicitly using the distribution. It's an instance of the notion of the idea of universality of coding. It's a universal source coding strategy, because it basically says, here's this IID source. We just use a very, very long sequence of these IID random variables and only encode for those. Only encode for the ones that we encounter. It's IID, it's independent, but we're encoding jointly. So that's one question I want to ask you. But before I ask you that question, the idea of universality is that we haven't actually explicitly used the distribution. We haven't actually used the probabilities. We used maybe, well, we're using this essentially the entropy to figure out how big the typical set is. But once we've got the entropy, we actually don't know what the probability is anymore. And the entropy says, in a sense, tells us what the typical set is. And then all these things that occur, we have a code word for them because they're the only things that occur with any probability. And then the second thing that might be a little bit strange to you, and hopefully you've thought about this or you're thinking about this, these are IID random variables, but we're encoding them jointly. We need to encode them in a sequence of length n together. If they're IID, why is it that we must encode them together?
Because we only have results for the distribution on sequencing. I mean,
well, here's the
partition property only goes for sequences.
Well, let me state it a different way. So, if each individual source character, right, and we're taking long sequences of source characters and making these things longer and longer in order to get the rate that we want down to the entropy. But why couldn't you just say, well, I have a probability distribution for each source character, right, p of x, right, and then compute the entropy of that, and why can't I just assign a bit string for each one of those and get the entropy rate? Yeah.
Is one reason that if you can't send a fractional bit?
Exactly. That's exactly right. Yeah. So the issue is that bits can't be fractional, right? So if I were, for example, let's say I had a source whose entropy was 0.25. Okay, so that would mean that on average, you should be able to use 1/4 of a bit per source message. But if you encode each individual source character using a bit, you're already using 1 bit per source character. So you, at the very least, you have to encode 4 of these original source characters together. Maybe that would be possible, but that's sort of a lower bound. In practice, you actually would need to code a much longer block than 4 in order to get that entropy rate. So things need to be coded together, not because there's any dependence amongst the random variables, but because when you have a code word, which is m bits, you want the m bits to represent the encoding of all of these things together based on the sort of property that the rate is an average over a numerator. It's a numerator and denominator. And in order to get back something which is a fractional number and not pay the rounding up to the next integer, you need to essentially look at the rate in terms of the average number of bits per source letter. So sometimes that's a little bit confusing. And if that's confusing still, then ask me again, because this is an important thing. Sometimes people say, well, this doesn't make any sense. These things are IID. You should be able to encode them separately. They have nothing to say. Knowing one doesn't tell you anything about the other. But it's for a different reason. Okay. So another thing I want to mention is in terms of the typical set. This is an interesting point that's made. The typical set is small, but maybe there's another set that's maybe smaller, or maybe there's another set that has more probability, or maybe there's another set that essentially, if it's smaller, we can actually encode it with even fewer bits. Is there a smaller set that has all of the probability effectively asymptotically? So in other words, is there another set such that for any epsilon, we can eventually make it such that it has all the probability? How do we know that that the typical set is asymptotically optimal? So we have all of the sequences, which is P of xn, right? Which is just xn, I mean. And we have the typical set, which is definitely smaller or equal to than all of the sets. But maybe there's some other smaller sequence, and let's call it, maybe it's B, and that's smaller than the typical set, and it also has all of the probability asymptotically. And maybe it's possible to encode only for this smaller set. You already know, for example, the typical set doesn't include the most probable sequence. Right? In fact, it doesn't include a lot of the most probable sequences. But maybe if we encode for this smaller set, we can achieve a slightly better compression rate. And what this next theorem shows is that that's not the case. That basically, asymptotically, the typical set is the smallest set that has all the probability. And again, this is an asymptotic result. So the result basically says, let's say that B delta is another set with all the probability. So it has this property for some other delta. And maybe it's more probable, or maybe it's smaller. And the theorem says that basically, if we've got this IID source, and we take any delta less than 1/2, and any delta prime greater than 0. So if this is true, if we're saying that eventually, for n big enough, the probability of this set of sequences has, all of the probability in terms of delta, then its size is no less than delta prime taken away from the entropy for any delta prime, no matter how small delta prime is. So we can make delta prime as small as you want. Eventually, when n gets big, that's going to have a size. This is just two ways of writing the size. Here's the actual bound on the size. Here's the actual statement of the theorem. But basically, it's a lower bound on the size based on the entropy and based on delta prime, which basically says that it's the same rough size. And so if we wanted to encode for this, we would again use, take the log base 2 of this, and we get nh bits. And so dividing by n, we get h bits per source letter again. So we get the same asymptotic rate. So there's no benefit for doing or searching for anything better than the typical set. Okay. So that's good. That's good news, right? Now there's some benefit for actually looking at the method of types, which we will do. Now the other thing I want to mention is this notion of the garbage can code. Remember we had this picture of the garbage can, which I mentioned again earlier today. So we had one length for the typical set, one set of code words for the typical set, another longer set of code words that encoded for everything. The typical set and everything else. The typical set was encoded for redundantly, but it certainly included everything else. And that code never had any errors because every possible sequence was coded for. And let's make a variation of this code and introduce errors. Okay. To say that, in fact, we're not going to bother at all with the typical set. We're just going to, we're not going to bother with the atypical set. We're going to throw those code words away. So what we're going to do, we could do something like this. Like we could say, well, the typical set is encoded to a code word, and then every one of the atypical sequences is also encoded to one of the code words that corresponds to a code word which has already been given one of the typical set sequences. So what do we do? So let's say, so it's a many-to-one mapping, right? Every one of these, there are no collisions here, right? So every one of these in the typical sequence has a unique place in the space of code words. But the atypical sequences is mapped to somewhere in this space, which is going to collide with one of the code words which has already been given an assignment from the typical set. That means that, let's say we find one of these and we want to decode it, we want to decompress. So what do? Well, we know that maybe there were two sequences that have been mapped to it, but what we just do is we say, well, I don't care about the atypical sequence. I'm just going to map, when we get this situation where we have a collision, we're just going to map to the typical sequence, even if it was the case that the original source string was atypical. Okay? And if that happens, then there's an error. There's going to be an error. And we can talk about the probability of the error because everything's probabilistic. And so what do you think is going to happen to the probability of error? It's asymptotically going to go to 0. So in some sense, we don't care because at some point the probability of the error is going to be so small that it's never going to happen for any purpose. And so the idea is that the code is not one-to-one. Source sequence might map to the same, multiple source sequences might map to the same code word. So what is the probability of error? Well, we know that the typical set has probability greater than 1 minus epsilon. And so the probability of error is upper bounded by the atypical set, which has upper bound of epsilon. Okay. So here's how we can do this. So basically, the notion of typicality in this particular case is using convergence and probability or limiting like argument. Basically, it says the following. This is sort of a little bit more precise than what we said before. For all epsilon and delta greater than 0, there exists some length, n naught, such that any length greater than that base length n naught is such that the probability of the sequence minus the entropy is bounded by, being less than epsilon is very, very large. Namely, it's bigger than 1 minus epsilon. Okay. And we can just flip this around and say, okay, well, what's the probability that it's epsilon away from the mean? Well, this is exactly the same thing. It's saying the probability that this quantity here is epsilon away from the mean, which is the entropy, and this is epsilon away, is upper bounded by delta. Okay. So we can think of this, and this quantity is really, in some sense, the error, right? But this is basically, this event here in yellow is an atypical event. This is when that occurs, that means that an atypical sequence occurs, and that is less than or equal to delta. And so we can think of this as a function of delta for n and epsilon. And what this means, this definition and the weak law of large numbers and the definition of the limit basically says that the limit as n goes to infinity of delta n and epsilon for any epsilon greater than 0 is going to be 0. So the limit is 0. So that basically means that n, eventually when n gets big enough, that's going to happen. And this quantity then is the probability of error. or at least it upper bounds the probability of error. Here's the error, here's the probability error, and here's delta, which is this delta n epsilon. So this basically means that the probability of error is going to go to 0 as n goes to infinity. So what this means is that regardless of whether or not we use a long code word and never have an error, or just don't even bother with the long code words and then experience error, the expected length is going to be the same. So if you remember in that set of equations we derived last time where we computed the expected length, I think it's also repeated here. One of the terms, the expected length that involved the long code word lengths, that whole term essentially became epsilon. That got as small as we want just because the long lengths were finite. But in this case, that whole term is not even there since we don't even code for that. So the expected length of this code, this errorful code, is still going to be the entropy. But there's going to be an error, but in this case the error is going to go to 0. And it's going to go to 0 exponentially fast in the block length, as long as we code at a rate greater than the entropy. So the theorem says coding is error-free if we use n h plus epsilon bits. So what if we use, well, here's a question. What if we use exactly, what if we set epsilon to 0? We've been saying epsilon is greater than 0. Maybe I should make that a problem set. What happens when epsilon is 0? What do you guys think about it? Sorry?
Or, I guess it would depend on the number of decimals in it.
That intuition seems reasonable. Anybody else have ideas? Not that that's a good idea. It has something to do with the numerics, and it has something to do with the special case. But I'll let you guys think about that. Right now, what we're going to do in class is concentrate on the epsilon greater than 0 case. Leave epsilon equal to 0 for you to think about, because that's sort of an interesting case. And in some sense, we don't yet have the tools to answer that. I think after we're done with source coding in like a week or so, we may be able to answer that more satisfactorily. But right now, there's some tools that we still need to answer what happens when epsilon is equal to 0. But what we can start looking at is when epsilon is less than 0. Okay, so suppose we use, for example, nh minus alpha epsilon bits, with alpha greater than or equal to 1. And alpha is just a sort of helper coefficient, which we're going to use to sort of help us scale. So basically, epsilon is sitting there. Epsilon is still greater than 0, but now we're subtracting alpha epsilon from h. So the number of code words we have now is asymptotically this quantity, right? Because we only have n h minus alpha epsilon bits, right? So that's the number of code words. Now the typical sequences are still sitting around, right? Typical sequences are still saying, okay, well I'm still typical, and I still have an upper bound probability of this. So, and we know that the typical sequences are all the things that happen. So now what happens is if we say, well, if we have the typical sequences probability is sort of changing as 2 to the negative nh minus epsilon at most. And the number of code words is changing with n as 2 to the n h minus alpha epsilon. And so if we multiply the two together, we essentially get the probability of things that can be coded. It's kind of like summing over all the things that can be coded of the upper bound of the probability. That normally that sums up to, that's a probability that at most can sum up to 1. Let's see what happens to that probability. So we multiply these two things together. Right? The count, which is the number of typical sequences, or an upper bound on the number of typical sequences, times the probability of each one of those things, gives us the total probability of us being able to code. And so what we end up getting is this. Okay, so that's the probability of being able to code a sequence. And alpha is strictly greater than 1. So what happens to that guy as n gets big? This is the probability of goodness, right? The probability of being able to code. What happens to that guy when n gets big? It goes to 0, right? So our probability of being able to code goes to 0 as n gets big. So that basically means, and it goes to 0 exponentially fast. And as soon as this, like, exponential growth is really funny. It's like, it either, if the exponent is constant, it just sort of sits there with n. But as soon as it gets above 0, it either grows exponentially fast, and if it goes below 0, it shrinks exponentially fast. So here's an error probability that's, well, I should say, this is a probability of codability, which is going to 0. So 1 minus that is the probability of error. So the error probability is going to 1 exponentially fast. So that means that as soon, and that's for any epsilon greater than 0 and any alpha greater than 1, so that we can make that as close as we want to the entropy. So we've got like the entropy here. Like as close as we want to the entropy, as long as we're coding at a rate greater than the entropy, we can do it, right? What happens right at the entropy? I'm not saying right now. And what happens below the entropy? It's bad. So there's like a sudden phase transition that happens right at the entropy. Everything's good, you're going along, you're getting a better, you're using longer and longer block lengths, but sure, you're coding, you're right at the entropy, right when you finally land at the entropy, you're in no man's land, because it's a little bit complicated what happens there. But then as soon as we go below the entropy, suddenly everything shoots up, the error probability shoot up to 1. This seems to be a fundamental change. It is, it's fundamental change. It's kind of like the threshold between which water turns from liquid to a gas, or turns from solids to a liquid. It's this point, and just everything suddenly changes. It's a fundamental property of this process. It's phase transition. It's a term from statistical physics. So the error goes to 1 as n goes to infinity. So that's kind of bizarre, right? So this has been, I think I mentioned this earlier on. People there have been companies in the past that have claimed that they, mostly these companies come from Florida. They sort of pop up in the middle of a bunch of a mango grove or something, and not I love mangroves. Mangoes are some of my favorite. Mangoes are my favorite fruit, but these companies tend to pop up among a bunch of mango trees and then claim that they've compressed down to below the entropy limit, and then they usually have some web page. And this has actually really happened. Sometimes they will have consultants from different universities around the world, which they've never actually consulted, but maybe they've gotten some sort of semi-verbal agreement at some conference at some point that they might potentially be interested in at some point in the future, perhaps if I have time, maybe, talking to you about a potential consulting possibility, right? I hope I've used the word possibility. The conditional form has been used enough in those sentences. But in any event, eventually these web pages, what usually happens is that the list of consultants starts shrinking and shrinking and shrinking as soon as the web page pops up to 0, and then the company vanishes. This has happened. And actually it was really perfect because a couple of years ago when I taught this class, there was a new announcement about one of these companies. And it just came out at the beginning of the quarter. It was just perfect. So every day we sort of took a quick look at the web page, and by the end of the quarter, the web page had gone away. It was perfect. But another thing that this says is like, why can't you run gzip or bzip multiple times on the file? If you compress a compressed file, it's not going to get smaller. If you keep doing it, eventually it'll just sit there at the entropy. I mean, actually, it'll get a little bit bigger because each time you compress it, it adds a little bit of bookkeeping stuff at the beginning. But if you take the raw bits inside of a gzip file, the data bits, you extract that and you try to compress it again, it won't work. It'll stay the same size. So there's this fundamental limit, which is the entropy. You can't compress down to more than that. And it's actually amazing. One of the algorithms that we'll talk about, I don't remember if we're going to do it this quarter or next quarter, but the Lempel-Ziv algorithm, which is the string compression algorithm, you can actually show that algorithm, even though it's purely algorithmic. It's basically just keeping track of pointers. It's like, how many times have I seen this string before? And it keeps track of pointers to previous instances of strings that we've seen. You can show, with a little bit of work, but not too much work, that that converges to the entropy rate of the source. Amazingly enough, even though it's just an algorithmic procedure.
Did you know that some people have found like fixed points for some of these compression algorithms? Like a file that, there's a file that compresses to itself. And so if you like double click on it to unzip it, just you get the same thing. You can do that for.
So here's a question. So let's say I take a uniformly random number generator, IID random number generator. It's Faircoin. I generate a big bit string of bits. Is that going to be compressible?
No.
And why?
Since entropy is equal to it's, or
Entropy is equal to binary, right? So what's the case?
No, the number of
Right,
the
so
length of
so the entropy is equal to 1. Right, so the entropy is 1. It's uniformly at random, fair coin. And 0.5, 0.5, entropy is equal to 1. We're not going to be able to compress it at all. Try it. Go home, write a little MATLAB script to generate a couple of 100,000 fair coin flips, save it to your file, run gzip on it, and see if it gets any smaller. Now, this is different than, of course, ASCII. It has to be true binary data. And obviously ASCII and binary, every time you have an ASCII character, you're using 8 bits per character. And so you can get sort of a one-time compression by using 1 bit per character rather than 8 bits per character. And so you can get a factor 8 compression. But I'm really talking about real binary bits. But, so it's uniformly at random at the bit level. And then conversely, if the random variables are compressed into fewer than nh bits, then it's virtually certain that information will be lost and and errors will occur. So that was the converse. Okay. So this is sort of restating what we've said. So we've proven, and now this isn't necessarily a good code. This is, in some sense, what Shannon proved in the early 1940s. There exists a very tantalizing statement. There exists a code that can achieve a compression rate of entropy plus epsilon bits for any epsilon prime greater than 0, as long as the block length n is big enough. How do you find it? Well, one way is to do typical sets. That doesn't mean it's a very good one. It's not a very computationally efficient one, but there exists a code. And so, since that time, it sort of started, the whole world of coding theory began. Like, how do you find a code? How do you find one that's computationally attractive and that's usable? The other theorem that he proves is this channel capacity theorem, which we're going to be talking about, which says that basically as long as you're trying to transmit information through a noisy channel below some critical point, which is called the capacity of the channel, then you can do so error-free as long as you use enough block lengths. The question is, how do you do a code? How do you construct such a code that achieves that rate? And to this day, people are still searching for codes that get exactly the Shannon rate, or close to the Shannon rate. There are very, very good codes now at this point. I mean, the ones that you use on your cell phones, for example, are extraordinarily good. But we'll talk about channels and transmission soon. But it's very dual. I mean, they're sort of duals to each other. So we already talked about this. Even though the source sequences are assumed IID, you must encode them jointly to achieve this rate. You know why now? And we use this many bits per typical sequence, and we use this many bits per typical sequence, this many bits per atypical sequence. Or alternatively, we just throw away the atypical sequences and get an error, but the error goes to 0 exponentially fast. And in either case, we get an expected length in terms of number of bits per source symbol of essentially the entropy. I had this up here because I was just going to remind you of something. Basically, again, this is saying that we're going to refer back to this in a minute, but basically, this guy is the one that has, when n gets big, This one has all the probability. But this is, I think, more relevant to the method of types, so I'll try to come back to this a little bit later in class. I think I've already said this before. Okay, so are there any questions? I'm actually going to take a break to see if I can recover my hard disk, which looks like it crashed again. I actually have 2 hard disks in here, and one of them looks like it's crashed. So, any questions? No questions? Okay, so let's take a short break and continue on. I'll have to look at the hard disk later. It's unfortunate, but I don't think this is related to why we lost the second half of the last lecture, but maybe it is. I don't know. But in any event, what we're going to do next is spend some time, and probably the rest of today's lecture, on the method of types, and then also maybe begin on the notion of universal source coding, which is described in this sort of section over here. Can't really see it. It's up there. Okay, so the method of types it's actually pretty interesting. It's sort of, in some sense, a refinement, maybe, of the typical sequence approach. It's a little bit more direct towards those sequences, and it gets at the issue of, for example, when the probability is binary and it's 0.5, we said that all sequences have the same probability, and so in some sense they're all typical, but the only sequences that are the ones that occur are the ones who have 50% ones and 50% zeros, and the ones that don't have 50% ones and zeros don't occur, or at least they do with astronomically small probability. And this sort of allows us to sort of answer those kinds of questions, and that picture of the binomial distribution as a function of k over n for different n's really is showing how the type of this sequence changes as a function of k, and how essentially only the sort of type, only one type, namely this one in yellow here, eventually is the only one that occurs. Again, paying attention to what's happening on the vertical axis. Considering how astronomically small these probabilities are getting. Even if we zoom in, you can see that eventually when n gets big enough, really this is all that's going to happen. This guy right here. And what guy is that? He's the one. Those are all the sequences who have 50% ones and 50% zeros. And we also saw that if we shift the probability over to 0.9, basically the same kind of thing happens. They all kind of shift over. Right. We saw the 0.9 case. So let's make that a little bit more precise with using the method of types. Okay. So what we're going to do is we have, again, n IID random variables, the same setup. It's going to be an alphabet size of some sort or another. And k is our alphabet size, and we partition, so there's all possible outcomes of this set of this sequence, right? So we know that there's k to the n possible outcomes, and we partition the k to the n sequences we partition the k to the n sequences according to the sequence's empirical distribution, namely its type. So type is going to be a word that we're using synonymously with histogram, or empirical histogram, or empirical distribution. So that's what a type is. And then the type class is really a set or a class of sequences of length n sharing the same empirical histogram. And we're going to see that the number of classes grows polynomially. In fact, not only sub-exponentially with n, but polynomially with n. Whereas the sizes, well, I should say, yes, sequences of the same type are equal probable, but the sizes of the type class, certain type classes in particular, are going to grow exponentially fast. So what does this mean? If the number of blocks of a partition grows polynomially with n, but some of the blocks in the partition themselves grow exponentially with n, it must be the case that some of those blocks are going to consume all of the probability, since when you consider all of the sequences and all of the blocks of all of the partition, they all must sum to 1. And that probably doesn't make sense initially, but it will hopefully eventually make sense. And this property, in addition to, in some sense, looking at the probability of errors and these combinatorics, these counting arguments, will allow us to bound the error, come up with a bound on the error, and do sort of a form of universal source coding. And we're going to get Shannon's source coding theorem and its converse in a very nice way, useful way. So that's sort of what we're going to do. So again, we've got n random variables. And actually, I lied before. So I'm using, for some reason, the letter D here. So it's a D array discrete random variable. So D was what we were using as K before. Maybe what I should do is change the earlier notation to D rather than K. But in any event, we have source messages that can take one of D elements. Yeah, I've got to fix this. It's no good when you change notation in midfield, is it? It's even worse when you change notation in mid-sentence. The K alphabet source symbol can take on no more than D values. It's a mid-sentence change of notation. Okay. Here's a statistic, which is called the empirical histogram of the sample. Actually, another notational change. Here I'm using lowercase n. This represents the number of times this symbol has occurred in this string. So obviously the biggest is going to be n. Before I was using uppercase n, and now I'm using lowercase n. But point is, how many times has A1 occurred in the string? How many times has A2 occurred in the string? And so on and so forth, all the way up to how many times has AD occurred in the string. When you sum up all of those times, it has to equal n, because it can, each one, it's itself a partition of the time. And then we divide by n, it's a probability, right? It's the histogram. It's full resolution histogram. Right? Every alphabet symbol has its own little bar. And this is called the type. It's also a probability mass function. It's a perfectly valid probability mass function where each probability is rational. And it's also a histogram, and we say it's the type. This is the type of the sample. That's what we mean by a type of the sample. And then we can actually think of it as a probability distribution. So P, the type, let's zoom in on this. Hopefully you can see it here. So this is the sequence. This is the empirical distribution associated with it. This is one particular symbol. And this is just this ratio. Okay. Now, how many different types are there? Well, first of all, let's have a notation to represent the different types or the different histograms. And let's say that script PM is a set of all possible types with a given denominator. So this is the set of all possible histograms that might arise in a sequence of length n for a D array alphabet. And there's a couple of notations you could use. We're going to the book, and we use sort of P then, but it's a function of x. So it's really a function of the alphabet size. But we're just going to use loose notation, and we're just going to write it as script Pn. But always implicitly, there's an assumed dependence on the alphabet size, D in this case. In fact, I could even write that. D. Okay. So here's an example to make it clear. Let's say that we are using a binary alphabet. So D is equal to 2. So these are all of the histograms that could occur in a sample of size n. So this first one would say that 0 occurred no times and 1 occurred all the time. The second would say 0 occurred 1 time and 1 occurred n minus 1 times. And so on up until the last one, which says that 0 occurred all the time and 1 occurred never. Those are all of the possible histograms. The denominator is always n. And we can see, just by looking at the count, there's going to be n plus 1 possible histograms from 0 to n for the first term. And if you're not familiar with this notation, you should be. So in general, what is fairly standard mathematical notation practice is to use curly braces to represent sets and parentheses to represent an ordered list. So here we have a set of ordered lists, and the ordered list is the histogram, because in the histogram, inside of each histogram, the order matters. But inside of the curly braces, you can commute the order, it doesn't matter. In this particular case, we've ordered it by the numerator of the first argument, but in some sense it doesn't matter, it's a set. So you should be familiar with that notation. Okay, so now let's say we've got a given P here. Now think of all of the sequences that have that type. That's called the type class. So the type class is a set of sequences of a given type. And so there's a couple of different ways of writing this. So the type class, written T of P, is equal to all sequences such that the type of the sequence is equal to the type P. Should I say that again? Say it again, yes or no? Yes. So it's all sequences such that the type of that sequence is equal to the given type of this argument here. Okay, so it's just the sequences that have a given type. Now you could say, oh, well, what happens if P is irrational or something? Well, we're going to get into that. Right now, assume that that's true. If P happens to be irrational, if P has irrational numbers, then the type class would be empty. Because basically all of the histograms for a given finite n are rational numbers. Right? So to get a non-empty type class, you have to at the very least have a rational type. And for a given n, maybe it doesn't even exist. Maybe you need to make n really, really big before you get even rational numbers that are equal. That doesn't matter. Type class can be empty if you give it the wrong thing. But this notation, T of P, is going to be used in this way. It's a function of the type. Okay, so here's a summary. We're going to see a lot of these notational summaries because this is sometimes a little confusing at first. So given a sequence of length n, we have, this is a typo. Given a sequence of length n, we have, number one, the type of the sequence, which is written this way. It's the histogram. Number two, we have the set of all possible types for sequences of length n. These are all of the possible histograms that could possibly arise from a sequence of length n. Of course, all of the types within this class are going to have rational values, right? Because they're all based on a numerator, which is a count, and a denominator, which is n. You can talk about a particular type in the set of all types. So P is a type that lives within here. And you can also talk about the type class. So for any given type P, T of P is equal to this. Not in the previous slide, if we restricted P to be within P of n. So suppose we took this and this together. If we took a particular type from all types for sequences of length n, could T of P ever be empty? No. Because by very definition, P of n, script P of n, are all of the types that could occur for sequences of length n. So if we choose any of the types that could occur for sequences of length n, and we look at the type class, those are all of the sequences that did occur, or that do occur with that type. So while it's well defined to put an irrational number in here, if a rational histogram in there, in general, if we take types out of this guy, it's not going to be irrational. Okay, so let's do a couple of examples. Alphabet size of 3, sequence size of 5, And here's the sequence. It happens to be 1, 1, 3, 2, 1. Okay. And this is an ordered list. So then the histogram is going to be 3/5, 1/5, and 1/5. So the denominator n is equal to 5. 1 has occurred 3 times, 2 and 3 have each occurred 1 time. Okay, so that's the type of the sequence. This is the type. And T of P x1 through 3, this thing, is the set of sequences with length 5 that have 3 1s, 1, 2, and 1, 3. So there are lots of them. There's this one, and there's also this one, and so on and so forth, and there's this one. Right? This is in lexicographic order. Each one of those sequences has the same type. So in other words, you could say, for all x of 1 through 5 in T of P, y of 1 through 5, the type of x of 1 through 5 is equal to the type of y 1 through 5. All of the sequences have the same type. So how many types? In other words, how big is the type? How big is the set of types? In this particular case, script Pn is of size 21. So there's 21 sequences that have a given type. Anyone want to venture a guess? How big is Pn? Script Pn. Well, here's the answer. It's even knowing the answer, it's a little tricky to see it. So it turns out that the exact size of script Pn is n plus the alphabet size minus 1, choose the alphabet size minus 1. The number of ways of choosing x minus 1 out of n plus x minus 1. How does that work? So this is a problem set that you will get, probably tonight. In fact, almost certainly tonight. But it turns out that this is a difficult, while this is sort of an interesting combinatorics, or I should call it, it's a combinatorial enumeration problem, and you should know how to do it. It turns out that that's tighter than we need, in the sense, what we're going to need, oops, how did that happen? What we're going to need is, getting better at jumping around, I think. So what we're going to need only is an upper bound on this that's much more amenable to manipulation. So then we've got this for now. So again, script Pn is the set of all types. And so therefore, if we take the union for all types of the type class of P, then that's equal to all sequences, right? Because it's a partition. I mean, each type class, has no intersection. So if P1 is not equal to P2, that implies that type P1 intersect type P2 is equal to what? To the empty set. One set of sequence has 3 1s, and another set of sequence has 4 1s. But those are different sequences, right? Okay, so we got the space of all sequences. So script x to the n is the set of all sequences. A particular sequence of length n is a dot. And so what the type class does is it partitions this set of sequences into blocks. I was I tend to watch video lectures at night, while everybody else is watching Breaking Bad. I watch academic lectures on techtalks.tv and Apple U and these other things. And there was a talk just last night, and the person kept saying, this partition is purple, and this partition is green, and this partition is orange. it's one partition. Okay, this is the notation. It was really bothering me. I don't know why, but it's one partition, and these are different blocks of the partition. A partition is basically a breakage of a set into blocks or into pieces that don't intersect. That's what a partition is. And so what this is showing is one partition, and we've got a purple block, an orange block, and a green block. Sorry. All right, pet peeve is over. So now you know that, but don't make the mistake. Okay. So okay. So the point is that the types partition all of the sequences into blocks correspond, and this is the type class for this type. And of course, there's no overlap. Now here's the bound that we need for this number of types. The number of types is upper bounded by n plus 1 to the x. Now, the important thing about this bound is, well, A, that it's a bound, but it turns out that it's not such a bad bound from the perspective of what we want to show, which is universal source coding ideas. And the important thing about this bound is, how does it grow with n? Does it grow exponentially with n? It grows polynomials. It's n to some constant. The alphabet size is fixed. I mean, sure, it's a higher order polynomial, but who cares? If I multiply that by some decreasing exponential, does that polynomial stand a chance as n gets big? No. Polynomial will be decimated eventually. No matter how slow that exponential is shrinking. So, and this is a much simpler bound. Remember, before we said the exact size of the type class was given by this choose thing. N plus x minus 1 choose x minus 1. Here it's an upper bound, but it's very easy to prove. And the way to prove it is sort of to break the histogram. It's basically saying, well, look at the numerators. You know, we have in the numerator, or look at the type, I should say, of a sequence. In the histogram, there's n plus 1 cells. Right? It's an array of length n plus 1. You know, for how many times each alphabet symbol has occurred, right? And we basically, did I say n plus 1? I meant that there are this many numerators. So, sorry, what I mean is that the value in the numerator is of size n plus 1. So any given symbol can occur either 0 times or 1 time or 2 times up to n times. Right? So the numerator can take on the value 0 through n. That's n plus 1 possible values. And there are x such numerators. And so if you just take a naive upper bound and you just count the number of possibilities there are, there's n plus 1 to the x, which is what we get. That ignores the possible interaction. Like if the first one is n, obviously the next one's not going to be, the next one has to be 0. So we're overcounting. But that's okay. It's an upper bound and it's still polynomial, and that's all we care about. Polynomial in n, that's the key point. And why? You know, even if it was a little bit worse, if it was still polynomial, it wouldn't matter. It would still allow us to show our theorem. What we're going to see, you know, this is sort of, first of all, I mean, it's easy to show that there's an exponential number of sequences, x to the n. Right? That's exponential in n. But it turns out that if, what this means is that when you go back to this picture, how many blocks are there? There's only, inside of the whole oval, there's an exponential number of sequences. There's an exponential number of these dots. But there's only a polynomial number of the blocks. So there's a polynomial number of these little colored checkered things, an exponential number of these dots. What must that mean? It means that at least one of the blocks has an exponential number of sequences in it. Aha, which one do you think that's going to be? That's starting to sound like a typical thing, isn't it?
The one which is close to the expectation.
Very good assumption. So this is hopefully going to sort of give us a clue as to what's happening here. We only care about the one that accounts for a majority of them, or at least all of the exponential growth. Let's see if we can figure out which ones those are in a quantitative way. Okay, so here's another summary, just to make sure we're on the same page. And don't say we didn't remind you again. So I'm giving you again, because if you say, well, I don't remember exactly what script PN means again, well, I'm going to tell you again. So you don't have any excuses. Okay, so don't ask me what this stuff means. Because again, I know the notation is a little confusing. So P, this is the type. It's the empirical distribution of the sequence. And this is a way of getting particular entry. I should change this to lowercase n here. Be consistent. This is the set of types with the denominator n. We're just going to use script pn for that, but you could also think of it as a function of the alphabet, or the alphabet size. This is the type class. It's the set of sequences that have a particular type. We have this theorem, which says that there's only a polynomial number of types, polynomial in n, number of types. And then we also know, it's just a fact, that this is exponential growth. This meaning this is exponential. Okay, now the first theorem we're going to show is that the probability depends only on the type, which is wording that the book uses, but we'll make sure that this is clear. So because we've been using P for the type and P of x of 1 through n as the type of a sequence, we're going to start using Q for the actual true source distribution. So in the past, in the asymptotic equipotential property, we were using P as the source distribution. So here we've got an IID sequence distributed according to Q. The only reason we're doing this is because we don't want to confuse Q with P, because we're going to be using P as types. Q might be irrational. Okay, we're not restricting Q. Right? A type for a given finite n is always going to have rational probabilities with the denominator n. Q could be anything. We could one coefficient could be, if we take the square root of 2 divided by n or something. We could do all sorts of crazy things. Times n. We can define Q however we want. And we can take the extension Q of n. This is just a notational convenience to be able to say, what's the probability of this sequence? Well, since it's IID, we just multiply together the probabilities of the individual items. We're making no assumptions about Q. So the probability of the sequence depends only on the type. What does that actually mean, even? So what does that mean is that the probability, in some sense, is independent of the sequence given the type and Q. So in other words, what this means is the following. This probability is 2 to the negative nh plus the Kolbach-Leibler divergence between the type and Q. Remember Kolbach-Leibler divergence? Does anyone recognize this? So what happens when n is going to get big? What's going to happen to this guy, do you think? Just intuitively, using AAP discussion, AAP argument. That guy's going to probably get really small, right? Because the type, again, this distribution here is always rational, right? This guy might or may not be rational. If Q happens to be rational, then at some point, P can essentially hit right on Q for n big enough, in which case that becomes exactly 0. But, you can, as the numerator and the denominator are allowed to increase, you can better and better approximate a given irrational number with a rational number. And so therefore, each one of these probabilities in this distribution Q can be better approximated by the corresponding probability in the type, and so therefore, if only the typical sequences happen, the ones that are roughly in proportion to the numbers given by Q, the type of that sequence, the type of the typical sequence, should be roughly equal to Q, and so the KL divergence is going to essentially go to 0. Or can, in other words, be made arbitrarily small for any epsilon. So that intuition is right, if you have that intuition. If you raise your hand if you have that intuition. Raise your hand if you don't have that intuition. Okay, so remember the typical, when n gets big, the only thing that happens are going to be the typical ones, right? The typical ones are going to be the ones whose fraction of, let's just say this is binary for the moment, just for the discussion. The ones whose fractions of ones and zeros are going to be close to the proportions given by this probability distribution Q. Because remember, everything's drawn from the true distribution Q. Q is our name for the true distribution source. Okay. This is the type, this is the empirical histogram of the sequence that happened. If the only thing that happens are going to be those things that have probability, have probability of ones, empirical probability of one, probability of zero, close to the true distribution, that means that this KL divergence is going to get small because the type is going to get close to the true distribution. And if the true distribution is rational or irrational, in both cases it's going to get arbitrarily close because we can better and better approximate irrational numbers with larger numerator and denominator. And the denominator is always growing, the denominator is always n, so that's going to always get bigger. And the numerator has the chance to also get bigger because it's between 0 and n.
Should that be Qn in that KL divergence? Oh, sorry, no.
But it's not to the n. It's just, remember, this is the histogram of the type. This is the extended distribution here. So very much like the AEP, the probability doesn't depend on the sequence anymore once we're given the type. Once we know the type of the sequence, and let's say that we know the type of the typical sequences, for example, then again, anything that happens has the same probability. But now it's sort of a little bit more precise because it's in terms of the KL divergence as well. So all sequences with the same type have the same probability. Now it turns out that even when this is small, when n isn't asymptotically large, 5.20 is still true. So this sort of tells us, the rate at which the KL divergence gets small tells us how close the probability is to 2 to the negative nh. So let's first of all prove this. Okay? So everybody understand the theorem? So this holds for a finite n, and there's no approximation. This is an equality. This is not a bound. Unlike before, this is an equality. Okay, so the probability of the sequence, according to the true distribution Q of n, is, because it's independent, just the product of the probabilities. And now what we're doing is representing it as the product over all possible alphabet symbols, A, times the probability of that alphabet symbol raised to the number of times that alphabet symbol occurred in the sequence. Here we're basically just using the definition of the type, and all this is doing is just getting rid of the denominator by multiplying the type by n, and so we're left with the numerator, and those numerators are the NA of the counts. The numerators are the counts. The type is always rational. This is a 2 to the log of something is equal to the something. So 2 to the log of Q n is a little funky, but it's basically just saying, this isn't clear, it's 2 to the log of A to the B is equal to A to the B is equal to 2 to the log of A to the B is equal to 2 to the B log A. That's all we're using. And that gets us 5.22. Now we're adding 0. This whole quantity on the right is 0. So we're taking out a factor of n. Here we've got type of A log Q of A, and then we're subtracting off type of A log type of A plus type of A log type of A. But now we can essentially, this is the product of 2 to the n, we can say 2 to the n times the sum, because if we bring the product up into the powers, we're just summing over x. And now suddenly this becomes entropic. This seems like an entropy. In fact, here we are. We're just taking the common terms, of P of A, P of A, and P of A. In one case, we've got logs of numerators and denominators. So this thing here turns into Kullback-Leibler divergence. Oops. And this part turns into the entropy. And we're bringing out a factor of -1. So there's the proof. And so again, it's an inequality. So in some sense, the Kullback-Leibler divergence gives us how far away the type is. I mean, from the perspective of coming up with a probability, how, depending on how close the type is to the true distribution, that sort of penalizes how far we are from the probability of that sequence being 2 to the negative n h. You know, notice the other thing that happens. As n gets bigger and bigger, p gets closer to q, and so this ends up becoming 2 to the negative n q, right? So I can sort of say that this goes to 2 to the negative n h of q with n, because the Kullback-Leibler is going to 0 and the type's going to q. So it's just like what we've known before, except that this is inequality all along. In fact, here's that theorem. If, in fact, q is a rational distribution, and if x happens to be in the type class of q, then we get this probability right away. Now, it turns out that q need not be rational, but when n is really, really big, x is, for all intents and purposes, up to epsilon errors, essentially in the type class of q. So we can add like plus minus epsilon, and it would be close enough. Again, thanks to the fact that n gets big. So this is already familiar with us. So if q is irrational, I think we've already said this. We can make the tail divergence as small as we want if we make n large. So here's here's something interesting. So the multinomial coefficient, the number of ways of choosing distinct alphabet symbols for every element, is n sort of choose, and so it's not really choose, but it's like n factorial divided by this first quantity factorial times this quantity factorial, and so on and so forth. It's just a generalization of binomial coefficient. And so this is exactly the size of this type class, right? But on the other hand, these choose kinds of things in factorials are not so easy to bound, and so we want to come up with a bound. And so the bound that we're going to have is something also that should look somewhat similar. It's basically saying that the size of the type class, rather than using 5.26, the size of the type class is upper bounded by 2 to the nhp and lower bounded by 2 to the nhp with some additional reducing factor, 1 over n plus 1 to the x. And again, the thing to note about this is how is it growing with n? Is it growing polynomially or exponentially? Growing exponentially. Even the lower bound is growing exponentially. Sure, the lower bound of the size of the type class is, we're dividing by a polynomial in n, but we're multiplying. So here's the divide by the polynomial in n here. And we're multiplying by this exponential in n. So the lower bound is growing exponentially fast, because the exponential is going to overtake the polynomial and eventually be all that matters eventually. So the lower and upper bound are sandwiched by exponential growth. So how do we prove this? Well, we start with 1. A lot of proofs in this book sort of start with 1 equals this, equals this, equals this, equals that. Or 1 is this and this, is this and this, which, these are these funny proofs. It's called the start by 1 proof. And so another start by 1 proof is to say, well, 1 is greater than, the extended probability of the type class, right? Because, this is a valid probability distribution, and this is a subset of the set of sequences. It's only the sequences that live within the type class. And so this is clearly less than 1. This is true for any probability distribution, so it's also true for the extended type. And here's just the definition of what this means. It means that we're summing over all sequences in the type class and computing their probability according to that type. And when we're considering sequences of that particular type, as we saw before, the Kullback-Leibler divergence between, I don't know, can you guys see this? Is it visible? Okay. The type, for any sequence of that in the type class, the KL divergence is going to be 0, and so we're given a probability of 2 to the negative h, 2 to the negative nh of the type. Right. That was from that statement we said before. And now we've sort of divorced the index of the sum from the thing we're summing, and so we can then count. Same trick we've always done. And we just count the size of the type class, and then its probability. We get its probability, and then we just get the bound. And this is just, if this isn't clear, in each of the sums, P is really the type of the sequence. P is meant to represent the type of the sequence here. And then, before we do the lower bound, let's do this lemma, which is actually kind of important. So what type class do you think has the highest probability when the generating distribution is a particular type? So now here's the idea. So if this doesn't make sense, we're choosing a particular type from the set of possible types. That particular type we're choosing is called cap P. And so that becomes, for the moment, our generating distribution. Now, under that generating distribution, when n gets big, which type is most probable under that type being the true distribution? That same one. But let's formally show this. So we're going to guess that this type class, T of P, has the highest probability under the type P. So here's the statement of the theorem. It's basically saying the probability of the type class, when the true distribution is this type, the probability of this type class of P is going to be greater than or equal to the probability under that type of any other type class. And the key thing here is that the extended distribution is sort of the extended type distribution. So this P of n here is the extended version of this type that we're choosing. There's another just little quick thing that we're going to show. I'm not going to explain it, but we're just going to assume that this is true. I actually have the explanation of why it's true down there, so you can look at it offline. But we're going to, this is saying that m factorial over n factorial is greater than or equal to n to the m minus n, regardless of whether m or n is greater than or less than each other. You can just go through that. It's all written there. So we're going to use that fact. We're going to use this fact in the following theorem, the following proof of theorem 5.4.4. And the proof of 5.4.4 starts with this ratio. And we're going to show that this ratio is greater than 1 or less than 1. Or greater than equal to 1 or less than equal to 1. To show this, greater than equal to 1. Yeah, so we have to show that this is greater than equal to 1. So we start with this ratio. And we write it in this way, which is basically a count of the corresponding type class times the probability of the sequences within that type class for both numerator and denominator. And they take the same form. And now the counts basically can be represented by this multinomial coefficient. Right. Both for numerator and denominator. We've done the same exact thing for the numerator and denominator. And the numerator and denominator have not interacted or canceled out with each other yet. But what we're going to do is, the first thing is we're going to cancel out the n. So this n is going to, and this n is going to cancel out. Because it's n factorial divided by n factorial. And then each one of these guys, these factorials are going to go in the numerator, and then these factorials are going to go in the denominator. And so we get these guys, and we get that for each a. And then what we're left with here is all of this stuff here just turns into this. Now here's where we use that bound from m factorial over n factorial is greater than m minus n into the m. Let me just say it to you again. We're going to use this thing, this yellow thing down on the bottom. M factorial over n factorial is greater than n to the m minus 1 factorial. So m is in the numerator, n is in the denominator, and then n becomes the base. And so we have, this takes the role of m factorial, this takes the role of n factorial. This stuff here is just copied over here. And then so we have I don't know if all these colors are useful for anything, but that's the numerator, here's the denominator, and so that becomes n again, and then the numerator becomes, and the denominator becomes this part here. And a lot of this stuff cancels out because we've got PA to the, like this and this cancels out with all of this, and what we're left with is the additional factor n raised to the n p hat a minus p. So we're left with this bit. Everything else, all that yellow stuff cancels out. And so we can just write this by putting the product up in the exponent, it turns into a sum, and suddenly everything is basically, we're just summing probabilities. And summing probabilities are 1. And so we get n to the n of 1 minus 1, so that whole thing is equal to 1, n to the 0. And so what we've shown is that this ratio is greater than or equal to 1, as we want it to. Hence, our results. Okay, now to prove the lower bound, it's kind of the same thing. The trick, there's a couple of nice tricks that you do, so maybe we'll go through it a little bit. So we start with 1, and we sum over all possible types that are possible for sequences of length n, and we compute the probability of that type. So again, the type, we're computing the probability of the type class of that type, so that's a partition of all the possible sequences, so that's definitely going to be equal to 1. But now what we're going to do is, rather than taking the probability of that particular type, we're going to take the probability, the max probability over all possible types for this thing. So that has to be bigger than the actual current one, right? And we know from the theorem that we just did that the max one is going to be under type P, it's going to be P. So this is the maximum. But that now has again divorced us from the sum. And we have an upper bound on the number of types from before, which is this polynomial. Remember this trivial upper bound. And this bit here is the same as this bit here. And we can bring out the polynomial. This is the same, bring it out of the sum. And we can, what we're left with is just the probability of one type class. And so what we do is sum over all sequences in the type class and compute its probability, which, since we're only computing sequences that lie within the type class of a particular type, we have the probability of that being exactly 2 to the negative nh of the type. And so everything again is divorced. We just have a counting. We've sort of done counting twice, right? So we've done counting here, an upper bound of the counting here, and we're doing counting again here. And then here's the probability. So what we're left with is this final result here. And so when we solve for T of P, we solve for the size of the type class, we get this lower bound. So in other words, we're showing all of this stuff is greater than or equal to 1. And from that gives us this. So let's look at this in a couple of other ways. In particular, let's just look at the binary alphabet case. And suddenly we have an upper and lower entropic bound for n choose k. Now, is this interesting? This is basically saying that whenever you want an upper bound for n choose k, you can just say, oh, well, it's no greater than 2 to the n h k over n, where k of the n is considered as a probability. So it's an entropic bound for a combinatorial quantity. And this happens a lot, actually. This is really sort of neat about information theory. In fact, chapter 17 of our book talks about a number of different entropic-based combinatorial bounds. And in this particular case, we got both an upper and a lower bound. And in the binary case, we can actually strengthen the bound. We can increase the lower bound by not squaring the denominator, and we still have a bound.
Can you actually approximate the entropy without first enumerating the set itself?
So if you took log of n choose k, I mean you can invert this bound and come up with an approximation of the entropy. Right? But I think what the point of this is to show that you can get bounds on combinatorial quantities by looking at its entropy.
I meant more that to actually compute the entropy, wouldn't you have to enumerate the set first?
Well, I mean, if you know the probabilities, it's easy to compute the entropy as long as it's a low-dimensional probability distribution.
Oh, right, yes. Yeah.
I mean, in general, if you don't, I mean, if you've got the you can get the probabilities from the counts, right? So you can easily compute the entropy. But what's interesting about this is that it's combinatorial. So, like maybe, for example, you don't have a good factorial function in MATLAB or a gamma function or something, but you can compute the entropy, and you've got log, and so you can come up with these nice bounds. You've got log and divide and multiply. If log is your only non-arithmetic operator, simple arithmetic operator, you can compute n choose k. Yeah, I want to try to finish this. So a little bit of notation. So when we say equals with a dot in it, this is a notation, sort of means equal up to the first power of the exponent, or the dominant power of the exponent. So basically what this really means is that the log ratio of an over bn, as n gets big, divided by n, goes to 0. So in other words, the difference between an and bn don't really matter when n gets big. And an and bn are sequences. And we take the log of the ratio and divide by n. The log of the ratio grows slower than n. So much slower that eventually it goes to 0. So that's what an is equal to bn means. So we have this theorem which basically says that if you take any type from the set of possible types in any distribution, which could be rational or irrational, the probability of the type class, these are the set of sequences that have that particular type P, under this true distribution, is essentially, up to the first order of the exponent, 2 to the negative n, called Bloch-Leibler divergence between the type and the true distribution. Or in other words, we have an upper bound and a lower bound, according to Bloch-Leibler. So remember, this is the probability of the type class. Remember that big oval that we had this sort of curve, this checkered pattern, and that we partitioned it into blocks? This is the question: is how probable is one of those blocks? So we choose one of those blocks, which is represented by capital P. How probable is that? Well, depends on, it's definitely going to be decreasing, but how fast it's going to be decreasing with n depends on the Bloch-Leibler divergence. Now, as you can imagine, as n is increasing, this quantity is going to be decreasing exponentially fast, right? But that's assuming that the Bloch-Leibler divergence is constant. In reality, if we choose a particular type, say like the most probable type, the Kolbeck-Leiber divergence is also going to be decreasing. So the question is what's happening faster? Is the Kolbeck-Leiber decreasing faster than n is increasing? That's the critical point that we want to ask and we want to wonder about. But before we get to that, let's just let's get to this theorem. So, the one thing we can say right away is that, if we sort of rank order those types based on closest to Q, next closest to Q, next closest to Q, and so on and so forth, the next closest to Q type is going to be decreasing exponentially faster in probability than the closest to Q type, just because of the difference in the Kolbeck-Leiber divergence. So how do we prove this? Well, we start, in this case, not with 1. We start with this. This is the probability under of the type class under the true distribution and its definition in terms of summing. We have the exact expression for the probability of a sequence of that particular type. It's 2 to the negative n times the Kolbeck-Leiber divergence and the entropy added together. Again, we've now divorced the index and we can start counting. And we count the size of the type class. And so we then use this previous bound that we had. This was the previous bound that we proved before. This bound is actually quite similar to what we used before. And we just use it inside of 5.47. And we're done. That's simple. But, the important thing I want is to, get the intuition of this, of what it means. It's a lot of notation. Okay, so let's summarize the basic theorems again. So again, I'm doing this a lot because I know it's a lot of notation. So the number of types with denominator n, it's growing polynomially in n, and our expression for this is n plus 1 to the x. The probability of probability of a sequence depends only on its type. Right. We have a bound on the size of the type class. It's growing exponentially based on the entropy of the type. We have the probability of a type class, which is essentially 2 to the negative n, the Kolbeck-Leiber divergence. So polynomial growth, exponential decay, potentially exponential decay, assuming that the Kolbeck-Leiber guys are constant, but they're not. So the question is, which types have the most probability? The ones that are closest to the true distribution. We know that. We already talked about this. And this property that says that, as I've said before, those types that are farther away will have exponentially and smaller probability than the others that are close. So here's our sort of type-based definition of a typical sequence. So we have a set of IID random variables, all drawn according to Q. Then we define our sort of type-specific typical sequence to be those sequences whose type is close to the true distribution. So it's another form of ball. It's all type classes, or all sequences of all type classes whose type is close to the true distribution. And by close we mean KL divergent, epsilon close in the KL divergent sense. So this basically now allows us to, I wonder if that's our next class. So this basically allows us to sort of talk about, in the case of uniformly at random fair coin probability flips, the types that have 50% ones and 50% zeros are going to be epsilon close. But the other ones that have 90% ones and 10% zeros, even though each element, each sequence within that type class has the same probability, that whole type class is not going to be typical. So it's in some sense, that's what I mean by it's more refined. we're sort of not including those other ones in the typical set anymore. We're only including the ones whose empirical histogram are close to the 2 distribution. I mean, in some sense, you could say this is the whole thing we're doing here is maximum likelihood parameter estimation using non-parametric probability distributions, histograms. That's really what this is all about. Law of large numbers. It's sort of maximum likely parameter estimation with non-parametric probability distributions in disguise. So, we're running out of time, and why don't I end? I wanted to get the end of this, but why don't I end here? And hopefully by Thursday I'll have a fixed hard disk. Okay, so any questions? Okay, so I will see you then on Thursday. Don't forget about your homework. It's due tonight.